All right, so today we're going to be talking about geometric sequences, which is the second type of sequences we've discussed so far in this course. So the goals that we have, we want to be able to distinguish between arithmetic and geometric sequences. We want to be able to write a formula that represents a geometric sequence and use a formula to calculate a specific term. So pretty much all the same things that we did with arithmetic sequences. So speaking of arithmetic sequences, we're going to do just a real brief review of what you learned about those. And we actually studied these twice, remember, once in Unit 1 and then again in Unit 3. So write a formula to represent this arithmetic sequence and use the formula to find the 25th term. So in this case, my arithmetic sequence 6, 11, 16, 21, 26, so on and so forth. So we can tell, remember, that something is arithmetic if there is a common difference. So meaning, if I do 11 minus 6, that gives me 5. If I do 16 minus 11, also 5. 21 minus 16, also 5. See this pattern? That's why we call it a common difference. So common difference in this case is 5. Remember that the other item that you always need to know to write the formula is the first term, which in this case is 6. Remember that our formula for the nth term, which we can either write a sub n equals or f of n equals, it depends on whether you're using function notation or not, but either way, it's always first term plus the common difference times n minus 1. And that doesn't change just because we might use an f of n notation. It means the same thing. So this is our formula. So if we go ahead to plug that in this case, let's just use the function notation. F of n equals first term, which is 6, plus common difference, which is 5, times n minus 1. Remember that sometimes they will write this in a simplified form, like distribute and combine like terms. So just make sure that you are on the lookout for that, as that could possibly happen. Next thing we want to be able to do is to find the 25th term. So that means they're telling us that n is 25. So I want you to use the formula, use n equals 25, and go ahead and find the 25th term. So that's the first thing I'd like for you to try on your own here today. All right, so let's go ahead and check your work. So to find the 25th term, that means we're just going to plug 25 in place of n. So we would have f of 25 equals 6 plus 5 times, and then here's where we do our plug-in, the 25 minus 1. So order of operations says we do it's in parentheses first, so 25 minus 1 is 24. So we do that first. Next comes multiplication. So I need to multiply 5 times 24. So 5 times 4 is 20, carry the 2. 5 times 2 is 10, plus 2 is 12. So 120 plus 6. So that gives us a final answer of 126. So if you didn't get that right, go ahead and correct it to make sure you have it right in your notes. All right, so a geometric sequence, at just a quick glance, looks like an arithmetic sequence. You've got numbers, and then you've got commas and ellipses, but there's a major difference. So look at and think about, if you were trying to make this an arithmetic, where would you go wrong? What's wrong with this? So hopefully you decided that there is not a common difference, Because if I do 4 minus 2, which is the difference between the first two terms, that's 2. But if I go between the third and the second term, 8 minus 4, that gives me 4, which means that this sequence cannot be arithmetic because I do not have a common difference. But that doesn't mean that there's not a pattern. It just means that it's not an arithmetic pattern. So in this case, instead of, like we did here, adding 5 every time, the pattern is that instead of a common difference, we have a common ratio. So instead of taking second term minus the first term, we do second term divided by the, so common ratio, we can do second term divided by the first term. That's why it's called common ratio, because ratio means to divide. Now the other way, and the way that most people think about it, is that you multiply by it. So what we did is we multiplied by 2. We multiplied by 2 again. We multiplied by 2 again, so on and so forth. Now, I would caution you against always thinking of it this way, because then sometimes when the numbers get smaller instead of bigger, you miss it. Because really technically what we're supposed to be doing is dividing. So second term divided by the first is what we will do to find that common ratio. So in example 1, we're going to identify whether the sequence is arithmetic or geometric, and then we'll write the common ratio or if there is a common difference. So when we look here at letter A, when I do 4 minus 1, that gives me 3. But 16 minus 4 is definitely not 3. So then we see if we might possibly have a common ratio instead, because this not equals means we do not have a common difference. So it's not arithmetic. So then I do 4 divided by 1 and 16 divided by 4. Those are the same. 4 over 1 is 4. 16 over 4, also 4. Check the next one because it has to work for all of them. 64 over 16, also 4. So that means that this is geometric. And the common ratio, which we'll call R, is 4. All right, so I want you to go ahead and try B and just decide if you believe it is arithmetic or geometric. Once you've decided that, then see if you can find your common ratio or common difference. So just decide on B, is this an arithmetic sequence or is it a geometric sequence? All right, so if we test it out, 81 minus 243 is a very negative number, like obviously way more than negative 100. If I do 27 minus 81, I definitely don't get over 100 in the negatives. So this is a no, so it's not arithmetic. And so then we'll look to see if it's geometric. So if it's geometric, I would need 81 divided by 243 to be the same as 27 divided by 81. So if I do that on my calculator, 81 divided by 243 comes out to 1/3. It reduces to 1/3. So 1/3. If I do 27 over 81, I also get 1/3. So far so good. It's looking like it's probably geometric, but again, you need to check all of them. So then try 9 over 27. This one's easier to do without a calculator because 9, they're both divisible by 9, and it is 1/3. And then finally, 3 divided by 9, also 1/3. So this is geometric, and R is 1/3. So this is why I cautioned you earlier against always saying that ratio is the number you multiply by. It is. That's absolutely a fact. But if we always think about it as multiplication, then sometimes students get confused when the numbers get smaller. It's because we're multiplying by a fraction and things are getting smaller. So that's why I always divide. Second term divided by first term. Third term divided by second. So on and so forth. All right, let's check C. So first I'll look for arithmetic. So 55 minus 80. So that'd be -25. So let's see if I do 30 minus 55. That's also -25. So is that also equal to 5 minus 30? Yes, sure is. So that means that this one is arithmetic because what I just found is that the common difference is 5. All right, now it is really important to note that it is possible to have neither a common difference nor a common ratio. In that case, the sequence is neither arithmetic nor geometric. So again, that doesn't mean that there's not a pattern to the sequence. There are plenty of types of patterns that are not arithmetic or geometric. So in this case, the pattern is that the first time I add 1, the second time I add 2, then I add 3, then I add 4, so on and so forth. I can come up with a formula if I work hard enough to figure it out that's going to work for that sequence, but it's not going to be the arithmetic formula or the geometric formula. So just because there's a pattern doesn't mean that it fits into one of these. So if on, the test you might be asked, is this arithmetic, is it geometric, or is it neither? And we have to be able to tell. All right, so speaking of formulas, just like we had formulas that we reviewed up here for arithmetic sequences, we also have formulas for geometric sequences. And so that's A sub n, same thing. So the nth term is first term times, instead of plus, the common ratio raised to the n minus 1. So in this case, we've changed our addition symbol here to multiplication. We've changed our D to an R. And we've changed our n minus 1 from being multiplied to being an exponent. Remember that this is the same thing in function notation as writing it like this. So these mean the same thing, f of n or a sub n. Again, a sub 1 is the first term in the sequence, r is your common ratio. So in example 2, we're going to write the formula for this sequence and use the formula to calculate the 10th term. So I'm going to set it up for you, and then I'm going to have you write the final answer. So first thing I look at is for a common ratio. So 6 divided by 2 equals 3. I need to check it. 18 divided by 6 is also 3. Yep. 54 divided by 18. Yes. Also 3. So that means that that's my R. Common ratio is 3. My a sub 1, the first term, is 2. So now all you need to do is to plug that in. So this time we're going to do a sub n equals, and I want you to finish. So plug in your a sub 1, plug in your R, and choose the correct formula for this sequence. All right, so hopefully you filled in your 2 first, since that's a sub 1. Then you put multiplied by, and then we have 3 raised to the n minus 1 power. So this would be the first part of our answer. Then it asks a follow-up question. So this is the formula. Then it says use the formula to calculate the 10th term. So that means it wants a sub 10 or f of 10. And so 2 times 3 raised to the 10 minus 1. So 10 minus 1, when you have something in the exponent like that, that implies parentheses around it, meaning you need to do that first. Then we do exponents. So our next step would be to do 3 to the 9th power, which is 19683. And then finally, we would multiply by the 2. So those PEMDAS are very important. We end up with 39,366 for the 10th term there. So this is our formula. There's our 10th term. All right, example 3, application to a real-life situation. In a population of fish, it is known that each fish infected by a certain virus will pass along to 4 other fish. 3 infected fish are introduced into a school of thousands of fish. The infection quickly spreads through the school of fish. Write the geometric sequence to represent the number of infected fish over time. So, when we start to write a sequence, we have to begin with our initial amount. So, our initial amount, 3 infected fish. That's telling me my a sub 1, so 3. Then it says each of those fish will pass the virus to 4 other fish. So 4 for the first one, 4 for the second, and another 4 for the third, which gives us a total of 12. So what I did was multiply by 4. Now I do the same thing again because each of these 12 fish now is going to pass it to 4 additional fish. So 48, and then we would continue the pattern. Represent the sequence as a formula. So that means either a sub n or f of n. I'm just kind of rotating, so I'm going to do f of n this time. Equals first term, which is 3, times common ratio. So r equals second term divided by the first term, which is 4, raised to the n minus 1. And there is our formula. So now we want to represent the number of infected fish as a table. So the term number, term 1, term 2, term 3, term 4. So first term, second term, third term, that's what it means there. So the number of fish would be 3, then 12, then 48. And then we'd have to multiply by 4 again, which is 192. So this would be our table. Then finally in D, represent the number of infected fish as a graph. So this is term number. You can see 1, 2, 3, 4. So this is basically how many, infectious stages there are. So at 1, we had 3 infected fish. So here's 10, so it's not even a quarter of the way up from 0. So infection stage is probably what we would label this. And then we would label this axis number of infected fish. So then 2 up to 12, so that should be a little more than halfway to the 20. Then I have 3 all the way up to 48, so big jump. So here's 50, so just a tiny bit below that. And then 4 all the way up to 192. So here's 190, little bit taller than that. And there we go. So if I want to connect, which it doesn't say that we need to, so just be careful that you pay attention to directions, because there are some times where we want the graph to be discrete, in which case we wouldn't connect. But in this case, since we see the pattern continuing, we probably would do that. So remember, a geometric sequence can also have a decreasing trend. We saw that here in example 1b. This was geometric, but the numbers were going down. So let's look at an example of that. Very similar to example 3, except we're decreasing. So a compost pile may reduce each week due to the decay of the organic material. The weight of the compost pile could follow the pattern 27, 18, 12, so on and so forth. The compost pile weighed 27 pounds at the end of week 1. Write a formula to represent the geometric sequence and use it to compute the 6th term. So I want you to take this guy right here. That's our geometric sequence. Find me the formula. So again, we're using this right here. Write the formula that represents this sequence for the compost pile. All right, so in our formula, we need the first term, which is 27, and we need the common ratio, which we always get by doing second term divided by the first term. Now, it's a fraction, and it doesn't come out nicely, so you need to reduce it. Leave it as a fraction. So these are both divisible by 9, gives me 2/3. 12 over 18 is also 2/3, so I know that it's right. So that means that my formula is going to be a sub n equals 27 times 2/3 raised to the n minus 1. Then it says use it to compute the 6th term. So that means a sub 6 is 27 times 2/3 raised to the 6 minus 1. So 6 minus 1 is 5. So 27 times 2/3 raised to the 5th power. So 2/3 to the 5th power, you can certainly do in your calculator. Does not give you a nice round number. Then multiply that times 27. And it gives you, as a fraction, remember that you can change them to fractions. It's 3.5 repeating, or 32 over 9. So our 6th term is either 3.5 repeating or 32 over 9. And it doesn't matter in this case which way you go, because it's a real life situation. So you are allowed to use a decimal in a real life situation. What does the 6th term represent? This is probably the most important question, is understanding what the answer means. 6th term, so 1, 2, 3, 4, 5, 6. This is what it would be. It represents at the end of week 6. So the 6th term represents the weight of the compost pile at the end of week 6. And again, we know that what that weight was about 3.5 pounds. All right, last one, graph this sequence. So when we want to graph this guy, again, you should always label your axes in a real life situation. So we have number of weeks here and pounds of compost. So week 1, we had 27 pounds. So week 1, 25. So halfway would be 27.5. So right about here, a little less than halfway. Week 2, we had 18. So a little more than halfway up there. Week 3, we had 12. Now, don't know what we had weeks 4 and 5 because we weren't asked to find that, but by week 6, we were down to 3.5. So this would be 2.5, so 3.5 would be like right here. So this would be, whoa, I apologize profusely. It is sometimes hard to use this very lovely pen, and I did not connect those very well. It should be a nice curve like what I had here, except one that is decaying or decreasing there, which we're going to talk more about in the next couple lessons. All right, so you make sure you've got everything written down in your guided notes, so that way you can use those to help you with your practice problems.